The final conic section that we're going to explore is the hyperbola. As a reminder, from the very beginning when we introduced all the conic sections, we had said that when you have this double napped right circular cone, right, so you got like two cones on top of each other, if you have a plane that intersects both the top and the bottom base, and it doesn't go through the center, you're going to get two intersection regions, one at the top and one at the bottom, and ultimately that figure that's formed is going to be called a hyperbola. So hyperbolas might look a little bit like they have two parabolas next to each other, but as we explore hyperbolas, we're going to find out that they have more in common with ellipses than they do with parabolas. So the definition is a hyperbola is the set of all points in the plane, the difference of whose distances from two fixed points, which we're going to be calling the foci, in the plane is a positive constant. So at this point in time, we're looking at the difference of the distances, whereas in an ellipse, the sum of the distances was a constant. Now the differences of the distances is going to be a constant. And that idea is going to be helpful for us to remember in the equation for the hyperbola. Since I'm looking at the difference of the distances, if we come down here real quick and look at this equation that we're going to be looking at for the equation for hyperbola, we're going to have subtraction signs in here. Whereas on an ellipse, we had a plus sign there. So ellipses care about the sum of the distances being fixed, and then hyperbolas look at the difference of the distances being fixed. When we talk about the difference of the distances, what's going to go on? So this is a sketch of hyperbola, but as opposed to having it tilted like that, maybe let's just orientate it so we can see a little bit better what's going on. So I'm going to kind of have these two curved regions curving away from each other in my final graph. So I still have two foci, and for all conic sections, they will eat their foci. So the foci are going to be inside of these curves. What's going on with these distance idea is grab any point that is going to be on the graph. So how about that point right there? If I look at this distance from the point to a focus, and this distance from the point to a focus, and I subtract those distances, and we'll just always just subtract them in the order of bigger minus smaller, that difference is going to be fixed. And that's true for all points that are on the graph. We end up with a hyperbola. The transverse axis is going to be the line that contains the foci. So since I have 2 points, they're going to be on a unique line. That line is going to be referred to as the transverse axis. The center of the hyperbola is the midpoint of the line segment joining the foci. So the center would roughly be about here. So we can see that it's not going to be contained like inside the graph, so to speak. The two pieces are going to curve away from that center. The conjugate axis of the hyperbola is the line passing through the center, and it's going to be perpendicular to the transverse axis. So sketch over here. Here would be the conjugate axis where it meets the transverse axis at a right angle. The vertices of the hyperbola are the points obtained at the intersection of the graph and the transverse axis. So here's my transverse axis where it hits the graph. Those are your vertices. And the vertices are a distance A from the center. So I'm still going to have this fixed distance A. That's going to be on the transverse axis. So maybe we can think about the transverse axis as being like our major axis. That's what we called it when we were dealing with ellipses. And the transverse axis is still going to deal with the distance A. The foci are a distance c from the center, where c squared is equal to a squared plus b squared. All right, so the distance to the foci from the center is c, where c squared is equal to a squared plus b squared. So a couple things. First off, we haven't talked about b at all yet, right? So what's going on with b is going to be a distance that we're going to go on the conjugate axis. And it's not going to get us anything like special for our parabola. So maybe I'll do that in this color. So on the conjugate axis, we are going to go up and down a distance b. And that distance is going to help us get something that's going to be called our fundamental box. So it's not going to be a point on the graph. We're going to use it. And that distance also comes into play when we go to find our foci. So a couple other things about this. When we were looking at an ellipse, the value for c was found by doing c squared is equal to a squared minus b squared. One of the ways that I remember what's going on with an ellipse versus the hyperbola is for an ellipse, okay, it ends with s, and so I remember that I need to subtract, okay, also with an s. For a hyperbola, it ends with an a, so that helps me remember that I need to add the two values, a squared and b squared. A couple of other things is that this c squared is equal to a squared plus b squared looks an awfully lot like the Pythagorean theorem, right? So a couple things. One is, where are these formulas coming from? The distance on the ellipse and the distance from the hyperbola, how you get to the foci. So it's a little bit of a long process to do the computations to derive those relationships. We can derive them. We can prove that this relationship holds true. Interestingly enough, you need to use the Pythagorean theorem to prove the relationship. But while the letters in both of these formulas are the same letters as used when we're usually talking about the Pythagorean theorem, this formula right here actually is not the Pythagorean theorem, right? Which is a little bit confusing, I know, because we're still using the same letters and it looks the same, but this isn't just like the Pythagorean theorem happening here, okay? These, the C, the A, and the B are slightly different in terms of the relationships and what's going on with the graph. So maybe we should have used different alphabet letters. As you move forward in math, you find that we start stealing letters from the Greek alphabet because we ran out of too many letters in all our alphabet. We're using letters over and over again, and it gets really confusing. But yeah, so this is, some students are like, oh yeah, I'm just going to use the Pythagorean theorem here. It looks like it, but this isn't actually the Pythagorean theorem. So, I know. Some things we just can't make it easy, huh? Alright, so, right, note up here. So the transverse axis was major axis, the conjugate axis, let me write a note up here, that can be thought of maybe as the minor axis. So let's summarize what's going on with these equations and what happens with the graphs then. So when you're dealing with a hyperbola, because you're looking at the difference of the distances being constant, we're going to have a subtraction here. Because of the subtraction, you're going to have one term being positive and one term being negative. If the x is the term that is positive, and we're always going to write the positive term first. So if the x term is the one that's positive, those ones will open left and right. Notice it's an and because you have the two branches. If the y is positive, so the y squared term is being written first, those ones will open up and down. So what is allowed to change is whether or not we have the x variable first or the y variable first. What's not going to change is that on the first term, regardless if you have x first or y first, on the first term you're going to have a squared, and on the second term you have b squared. So remember, for an ellipse that was a little bit different, right? For the ellipse you had to figure out whether or not a was on the x or the y, because it always had to be associated with the major axis. That's not going to happen on the hyperbolas. The a doesn't move from the first term. What's going to be possibly moving is which variable occurs first. So some sketches down here. So let's put in x and y axis, we'll have a parabola opening left and right. We'll just make this one easy. We'll have its center being at the origin. So in this case, my transversal axis is going to be parallel to the x-axis. Because this one in my sketch is centered at the origin, the transversal axis is the x-axis. But if the center moves, if it's a different hk, but x is positive, then wherever the transversal axis is will be parallel to the x-axis. So remember, your vertices are on the transversal axis. Remember, your foci are on the transversal axis. So then the distance from your center to your vertex is a, and then associated with the other variable is going to be the distance that you go on your conjugate axis, which is going to be b. These two numbers are going to be helping us build this, I'll write it down here, fundamental box. Okay, so for however far A is and however far B is, okay, we're going to go left and right, up and down. And the reason why this is going to help us is that hyperbolas have some asymptotes. And if we look at the general structure for the asymptotes, notice that this is written in point slope form. And we usually leave it like that so we can read off all of our important information, right? Here is going to be our center, and then the B and the A have meaning in terms of what's going on with the distances that's going to be happening on your two major axes. So when we draw, while we're drawing this fundamental box is where the corners are, we're going to draw in our diagonal. And that should have gone through the center. Let me draw this a little bit better. Let's move this, as probably should have sketched it after I put in my asymptotes. Right, we'll do it at the other side as well. Alright, so I'm going to have these two asymptotes that then this curve is going to approach and flatten out. So this is another reason why it's not going to really be a parabola, is that you're going to have a lot of curve here, but as it gets further and further away from the vertex, it's really going to straighten out and almost turn into a line as it heads up. So let's look at if the y is the positive one, what would that look like? So this one is going to open up and down. So I would still have my value for A, which is going to get me to my vertex. I'll still have this value for B, which is going to be the distance I go out on the other axis. Whatever those distances are. Try to approximate them here. Okay, I'm going to be able to sketch this fundamental box. I'm going to be able to build in some asymptotes going through the diagonals. Okay, we'll also go through the center, so there are my asymptotes, and then if the y is positive, then these are going to open up and down, right? So if this is my vertex, here's going to be another vertex. So as this opens, it'll just start approaching those asymptotes on the outer pieces, and it's going to come in and grab that vertex. All right. Maybe the last thing to add to these is to remember that the focus would be inside the curves. With all that, let's take a look at a few examples where we're given our equation for a hyperbola, and let's find all of these important characteristics and ultimately graph it. So some things to notice right away is that the y value is positive. So this thing will open up and down. Generically, just because we just looked at this, it might help to always write down that generic form. So a up and down opening hyperbola will have the structure of y minus k squared over a squared minus x minus h squared over b squared is equal to 1. Oh, that's an important thing. Maybe we'll make a note up here. Just like the ellipse, it's always going to be a 1. Okay, so we know that this will have this kind of generic structure. Notice that you don't really have anything being added or subtracted next to those variables. So that tells me my center is going to be at the origin, 0, 0. My value for a is always underneath the positive variable, whatever that first is. Okay, so a is under that positive variable. We always write that positive variable first. So in this problem, my a squared is 1, which means my a is 1. And my b squared is equal to 15, so my b is equal to the square root of 15. And to help me with graphing that, we should probably get a decimal approximation that's going to be roughly 3.9. Let's go ahead and get values for c, which is going to help me with the graphing of the foci and finding out where they are. So the general structure is c squared is equal to a squared plus b squared. So c squared is equal to, well, my a squared is 1, and my b squared is 15. So c squared is equal to 16, which means c is equal to 4. Okay, so my foci are going to be 4 units away from the center, and then because I'm having y as the main variable, it's actually going to be going up and down. Let's go ahead and graph what we have so far. We've got a lot of information here. Let's see what we're working with. All right, so I need a center at 0, 0. We're going to be going up and down 1, left and right 3. So let's put in a couple tick marks here. All right, so the center is not going to be actually on the hyperbola, right? But it helps to maybe mark it so that way you know what's going on with respect to that. The A is going to get me my vertice distances. So since my A is 1, we're going to go up 1 and down 1. Right? It's associated with the y variable. So let's go ahead and record those. My vertices are going to be, all right, so it's going to be 0, and then I'll just write it as plus or minus 1. Maybe at this time, let's note that because it's going to be opening up and down, this is where the vertices live, and this is where the foci are going to live. So my transverse axis is going to be parallel to the y-axis. Now, because the center is at 0, 0, it's actually the y-axis in this case, but when we talk about it in more general, centers elsewhere in the coordinate plane, we just look at, for the transverse axis, who is it parallel to? Is it parallel to x or parallel to y? So what do I have so far? I know where my center is. I know where the transverse axis is. I know my vertices. Let's go get the foci. So I know how far I need to go from the center to get to them. I need to go 4 units up and 4 units down. Okay, so that is going to be one of them. And that's the other. So the foci are going to be at 0 and then plus or minus 4. Now I know that this thing's going to open up or down, but I should be really getting those asymptotes in order to help me with my graph first. So using my values for A and B, so A is going to be going up 1, and then B is square root of 15 or 3.9. So if I just kind of make a little mark, there is going B out to the left and the right on that conjugate axis. So using those values, I can make my fundamental box. All right, cool. So then I can sketch in my asymptotes. So what's going to happen is if I just go ahead and draw a line, we'll do a dashed line through the diagonals, or through the opposite corner, so a diagonal, that is going to be the asymptote, and it's going to go through the center. So we'll do it on the other side as well. Alright, cool. So now that I have those, I can sketch my graph a little bit better, right? So there's its vertex. It's going to be flattening out, and then it's going to approach those asymptotes. So there's the upper branch of the hyperbola, and here's going to be the lower branch. Maybe let's make that a little bit closer to there. There we go. Let's get the equation for those asymptotes. Okay, so it's going to be through 0, 0, and to just done grabbing one of them, I had to rise 1 and run square root of 15, right, to get the positive sloping asymptote. Okay, so that gives me a slope of 1 over square root of 15. And I'll simplify that in a moment because we don't normally like to leave those radicals down there, but just that tells me what's going on in terms of the A and the B value. And then, but I also have this one that's going down, right? So the one that's going down, that one will rise -1 and run square root of 15, however you want to think about it. So that one is just going to have the negative version of that slope. So if I go to use my point slope form, I don't really need to because the center is at 0, 0. So the equation for the asymptotes are going to be y is equal to plus or minus 1 over the square root of 15x. So then to just finish this, I'll rationalize this by multiplying both the numerator and denominator by the square root of 15. So I'll get plus or minus square root of 15 over 15 and then x. So those are the equations for my asymptotes. And I know there's already enough going on with all of these conics that you're like, really? We're going to start bringing lines into this too? Yes, we are. So you can't ever get rid of anything in math. We keep it all. So now we've got to worry about finding these asymptote lines using our point slope form. All right, so for our next example, what's going to happen on this one is we are going to shift the center. So notice on this one, since the x is first or the x is positive, this one will open left and right, which means then my transverse axis is going to be parallel to the x-axis. So for this one, h is still going to be associated with x, k is still going to be with y. So this one will have a center at 3, 1. And my a value is going to be on the x-axis. So again, because that's first, it's always going to be associated with a. So a squared is 25, which means a is 5. So b squared is 4, which means my value for b is going to be 2. Let's go ahead and get our value for c. So c squared is equal to a squared plus b squared. So c squared is equal to 25 plus my b squared is 4, or 29. So my c is equal to the square root of 29, which is roughly about 5.4, right, to help me with my graphing. So I have a lot of distances. Let's go and get some points. Let's find out what's going on with my graph. So my center is going to be at 3, 1, and then I need to go 5 units left and right from that on the x-axis, 2 units up and down from that on the y-axis. So it kind of gives me an idea about what parts of my graph I need to sketch. Need more x, more positive. Okay, so my center being at 3, 1. So maybe I'll mark that in yellow. Right, that's not actually going to be on my graph, but I need it to figure out the other distances. So from that point, we're going to go 5 units on the x-axis left and right. So I need to go 5 more units on that. So this would be 4, that would be 8. All right, that's 1. I need to go at least 2 units up. Let's go down a little bit. And then from my center, I need to go 5 units to the left. So 1, 2, 3. I need to do at least 2 more. Let's add a couple more for good measure. All right, so from my center, 5 units to the right gets me this point. 5 units to the left, 1, 2, 3, 4, 5, gets me that point. So who are those points? So for my vertices, with relationship to my center, I'm only moving left and right. I'm not going up or down. So the y-coordinate will not change. What's going to change is the x-coordinate. So this one is going to be at 8, 1. And then this other one, vertice is going to be at -2, 1. So I have my vertices. Let's go ahead and plot the foci. So for the foci, I need to go out square root of 29, or 5.4 roughly, from my center. So 1, 2, 3, 4, 5, and a little bit more. That's going to be one of my foci, 1, 2, 3, 4, 5, and a little bit more. That'll be my other one. So the foci, again, I have no movement up or down with relationship to the center, so it's going to still have 1 for the y-coordinate. What's going to matter is for the x-coordinate, and we're going to write this exact. So with relationship to 3, we either added or subtracted the square root of 29. We can just leave it right like that. So those are the coordinates for the foci. To finish the graph, let's go ahead and figure out where those asymptotes are. So for my asymptotes, this is not going to be through the origin anymore. It's now through my center. Three, 1, and we need to figure out the slope. So from my center, all right, so let's go ahead and make that fundamental rectangle. So from there, I'm going to go 5 units out. Right, and that's how I got my vertices. And we're going to do 2 units up. So 1, 2. And then we're going to go down 1, 2. So that is going to get me my fundamental box. Let's go up a little bit, then over. Here's where if I had lined paper, that would have been a lot easier. Okay, so what's going on with that? Center is at 3, 1. Okay, so my slope. Okay, so from my center, if you want to think about it, you went up 2 and over 5. Or you could have thought about it being going down 2 over 5 if that's the negative sloping line, so it's going to be plus or minus 2/5. So a reminder, we use point slope form, which is y minus y1 is equal to m parentheses x minus x1. Let's plug in our y coordinate we know, which is 1. The slope is plus or minus 2/5. And then my x coordinate is 3, so we'll substitute all that information in there. And we're just going to go ahead and leave it like this. Leave it in this point slope form because I can see a lot of really cool information, right? I can see the center and I can see what's going on with my a and b values. So that's fine for this point. So let's finish our graph. Okay, so we're going to go and that's from me freehanding this. It's not going to go quite through the center smack dab like it's supposed to. I'll just maybe move that center so it looks like it does. Okay. We'll fake it. This is why we use programs to help us with the graphing. It's hard to freehand all this stuff. Okay, so there's going to be my asymptotes. They should be going through the corners of that fundamental box, through that center. There's the vertex. It's going to eat that focus. I'll draw in the branches. Excellent. All right, very good. So for our next example, and you knew this was coming, we are going to complete the square on this. So this one, it may not be so obvious what we're even looking at to graph if we're given it. I mean, obviously in this section we're talking about hyperbolas, but in general, like on a test or just out there in the universe, if we're given an equation look like this, we want to have an idea about what it looks like, right? We talked about the functions and having that prototype in your head. So the key thing on this one is to notice that both x squared and the x variable and the y variable are both squared, right? So this isn't going to be a parabola because in that case we would only have one squared variable. So now I'm starting to whittle it down to, okay, it could be a circle, it could be an ellipse, it could be a hyperbola. But the other key thing is that one of the variables is going to be negative and one of the other variables is going to be positive. So that's going to let me know, hey, I'm in the case where I'm going to be dealing with a hyperbola. Okay, so let's take a look at this guy. So it's 2y squared minus x squared plus 2x plus 8y plus 3 is equal to 0. So the positive term is always, or the positive variable is always going to be first. So I'm going to leave the y pieces first. So 2y squared plus 8y. I'll have the x variable pieces next. So minus x squared plus 2x. And then we're going to move this constant to the other side, so equals negative 3. Now to complete the square on each one of the squared pieces, I need the coefficient to be 1, so I'll factor off a 2 from the y variables. So I'll be left with 2 parentheses y squared plus 4y plus some number that I need to find. And then for the x variable to complete the square, I don't have a number sitting there, but I have that negative sign. So I got to factor out that negative sign because I want this to be positive when I complete the square. So I'll have x squared minus 2x plus some number that I need to add. And on the other side, I have that negative 3. Let's find those special numbers. So for the y variable, I'll have 4 divided by 2, and then square that. So 2 squared is equal to 4. That's what I need to put in the blank. But on that side, I really didn't add a 4. I added an 8. Right? So I'll need to add an 8 to the other side. And then for the y variable piece, I'll have negative 2 divided by 2 and then squared. So negative 1 squared, which is 1. Right, so I need to add a 1 right there, but it's really going to be negative 1 that I'm adding because of distributing that negative sign through, so that's what I'll have to do on the other side, is subtract 1 to keep everything in balance. Cool. Let's go ahead and finish factoring this. So I'll have 2 parentheses y plus 2 squared minus, and then x minus 1 squared is equal to, let's see, that'll be 5 minus 1 or 4. Now the next thing is we need this to be a 1 on the side. So we'll divide everybody by 4. So I'll have y plus 2 squared over 2 minus quantity x minus 1 squared over 4 is equal to 1. So now I have this in my form that I need. So now that I have this, I know a lot. Since the y is squared, right, that means my transversal axis is going to be parallel to the y-axis. I now know my center. So this guy's center is going to be at 1, negative 2. Remember, your h is associated with your x variable and your k is associated with your y variable. I know my a squared is equal to 2, so my a is equal to the square root of 2, which is roughly about 1.4. And my b squared is equal to 4, which means my b value is equal to 2. And notice that a is not always bigger, right? A is associated with the positive term, whatever the positive term is. So that value for a could actually be smaller than the value for b. That's okay. So given all of this, let's go get our value for c. So c squared is equal to a squared plus b squared. So for this problem, that's going to be 2 plus 4, or 6. So that means c is equal to the square root of 6, which is roughly about 2.4. All right, we have a lot so far. So let's go ahead and start plotting this. Figure out what's going on with our points. So my center is going to be at 1, negative 2. Okay, so 1, 2, 3, 4, 5, 6. And if you have graph paper, it's so much better to do these actually using graph paper as opposed to trying to freehand the stuff. So go ahead and grab it if you have it. Otherwise, just include the sketch, but take some time to make sure that things are spaced out. But it's so hard if you need a little bit more space in your graphing and you're like, oh, I need a little bit more room. All right, so I have my 1, negative 2, that's my center. From that, my a value is going to be 1.4, and it's going to be on the y-axis. So 1.4 up, 1.4 down. Those will get me my vertices. So let's go ahead and record what I got there. So my vertices are going to be at, alright, so with relationship to my center, I'm not moving left or right. So I'm still going to have 1. What's happening is I'm moving up or down from this point. So from -2, I'm moving up and down a distance of square root of 2. So that's going to give me my vertices. Let's go ahead and put the foci down. So from my center, I'm going to go up or down a distance of square root of 6, which is about 2.4. So 1, 2, and then 0.4. That's going to be one of my foci. And then 1, 2, and yep, I need to extend this a little bit further. Alright, so let's try this again. So 1, 2, and a little bit more. Alright, so there's going to be my other focus. So my foci are going to be at 1, again, because I'm only going up or down, not left or right. And from -2, I'm going up or down a distance of square root of 6. So now I have my foci. Alright, so let's go get those asymptotes. So to do that, I'm going to need that b value. So from my center, I'm going to go 2 to the left, 2 to the right, and then using my a value, which was that 1.4, I'm going to sketch in my fundamental box. So what's going on here is for the asymptotes, we will have a center of 1, -2, a slope of plus or minus. So I went up square root of 2 and over 2. So the equation will be y plus 2 is equal to plus or minus square root of 2 over 2 x minus 1. So those are the equations for the asymptotes. Now let's go ahead and sketch them in. So from the diagonals of my fundamental box, we'll extend those out. It goes through the corners, it goes through the center. Let's try this up here. There it goes. Okay, so I now have everything I need. So from the vertices, we'll extend that out till we get to our asymptotes. Alright, lots of work, but we built that graph. Okay, so now we're going to shift gears. We'll start looking at examples where we're going to play the detective game. We're going to be given some conditions about what's going on with our hyperbola. And we need to find the equation that satisfies the stuff that we're going to be told. So the first one is we are told we have a focus at -4, 0 and vertices at -4, 4 and -4, 2. So first thing I'm seeing is lots of stuff happening at -4. So let's see what's going on. You do not need to sketch a graph in order to solve these, but I strongly encourage it. So I've got -4, 0, -4, 4, and -4, 2 that I need to put on here. So 1, 2, 3, 4. 1, 2, 3, 4. Okay, so at negative 4, 0, I have a focus. I have a vertice at negative 4, 4, and at negative 4, 2. Right, and that's all they gave me, so I got to be able to break this down and figure out what's going on. So first helpful piece of information would be to maybe get the center. So remember, the center is halfway between those vertices. It's actually halfway between the foci as well. But I have both vertices. So if I'm at negative 4, 4 and at negative 4, 2, and I want to go halfway, well, the distance between these two is 2 units, so halfway is going to be 1 unit. So my center is going to be at negative 4, 3. So that's going to get me my H and my K. Maybe another thing to recognize just from looking at our graph is based upon where the vertices are and the focus, and remember that this all needs to be on that transverse axis. So that means my transverse axis is going to be parallel to the y-axis. So the y term is going to be first in the equation. So just general structure is going to be y minus k squared over a squared minus x minus h squared over b squared is equal to 1. So far, in order to find this equation, I know what my h and I know what my k is. So let's go get some distances. So the distance from the center to the vertex is a. So looking at this, if here's my, we need this, so maybe I'll just go ahead and label it. There's my center, there's my vertex. So this distance right here is a, so a is 1. Which means a squared is 1 when I go to put it into my equation. The distance from the center to the foci is c. So from my center, and I was given a focus, so whatever this distance is right here is going to be c. So c is equal to 3, which means c squared is equal to 9. If I know a and b, or sorry, if I know a and c, I can get b, because relationship is c squared is equal to a squared plus b squared. Right, on a hyperbola, we add these. So my c squared is 9. My a squared is 1. Okay, so I'll then solve this for b squared. So subtracting 1 from both sides, we get 8 is equal to b squared. And you know what? I could take the square root of both sides, but I don't really need to, because I need to find this equation, and I need to know b squared, and I have it. So let's see what we've got. So I'll have y minus 3, because I want my k value, squared, over my a squared, which is 1, minus x minus negative 4 squared over my b squared value, which is 8, is equal to 1. So we just substituted in our h, k, a, and b values, and we're just going to clean this up a little bit. So I don't need to divide this by 1, right? So I'll have y minus 3 squared minus x plus 4 squared over 8 is equal to 1. And there is my equation. So the sketches really help because there's a lot of information going on, a lot of distances happening, and it's really easy to get kind of backwards on those. So, all right, let's take a look at our next example. So for the next one, I'm told that the center is at 1, 4, the vertex is at 0, 4, and the focus is at negative 2, 4. So again, seeing lots of 4s here. That's telling me some information about what's going on with that axis. The center is going to give me my HK. Let's go ahead and do a quick sketch to see what's happening here. So so I know I need a lot of stuff at 4, right? So 1, 2, 3, 4 on my y-axis. Okay, so my center is going to be at 1, 4. I have a vertex at 0, 4. I have a focus at -2, 4. All these pieces of information are telling me that my transversal axis is parallel to the x-axis. Which means in the general structure, the x is going to be first. Okay, so let's just talk about general structure. X minus h squared over a squared minus y minus k squared over b squared is equal to, you guessed it, 1. So I already have my h and my k because they gave me my center, so thank you for that. So I just need to get my a and my b values to finish this guy off. Alright, so looking at this, so this was my center, right? So the distance from the center to the vertex, which in this case looks like, so that's going to be 1. Right, that's my value for a. So my a squared is 1. The distance from the center to a focus is going to give me my value for c. So this is going to be, what is it, 1, 2, 3 units. So my c squared is 9. And given all this information, I can get my value for b, because c squared is equal to a squared plus b squared. So 9 is equal to 1 plus b squared. So I get 8 is equal to b squared. And again, I can just leave that because that's exactly what I need in my formula. So let's come over here. X minus 1, the x coordinate of the center, over my a squared value, which is 1, minus y minus my k value, which is 4, over my b squared value, which is 8, is equal to 1. And then to clean this up, we really don't need to divide by 1. Oh, that's supposed to be a squared on there. So there is the equation for my hyperbola. Alright, so last example. How we doing so far? We doing okay? Alright, excited to wrap up our last example from our conic section. Alright, so here we go. So we are told that we have foci at 0, -2, and 0, 2, and an asymptote at the line y is equal to -x. Alright, so this is a little different. They didn't give me the center, but I know information about the foci, so that's going to tell me a lot. So let's go ahead and sketch in some axes. Make this a little bit bigger. Alright, so sketch of what's going on, 0, -2. I like to do my foci in red. makes them stand out to me. They're important. All right, so here is one of the foci at 0, -2. The other one is at 0, 2. So first thing to remember is the foci lie on the transversal axis. So this must be my transversal axis, which tells me, because it's parallel to the y-axis, in this case it actually is the y-axis, but that's who it's parallel to, that's going to be the variable that comes first. Okay, so general structure is going to be y minus k squared over a squared minus x minus h squared over b squared is equal to 1. All right, so next helpful tip is to remember that the center is going to be halfway between those foci. Okay, so if these are my two foci, my center is going to have a y-coordinate of, an x-coordinate of 0, because it's still going to be on this transversal axis, but halfway between these, so it's going to end up actually at the origin, 0, 0. All right, so really easy center, gets me my h and k. The last thing I need to figure out is my values for a and b. Now they didn't give me any of that stuff, but they did give me c, because c is the distance from the center to the foci. So if my center is here at the origin, then this distance here, which is c, has got to be 2. Now, they also told me about the asymptote as being y is equal to -x, right? That's one of the asymptotes. So remember that the 1 is implied here. Right? So the slope of this guy is -1. So that's going to be negative whatever my a and b values are that I'm trying to find. So multiplying both sides by -1, we get 1 is equal to a over b. Clearing the fractions, multiplying both sides by b, we get b is equal to a. All right, so whatever the value for a is, that's going to be the same value for b is. So now we're ready to pull all this together. If c squared is equal to a squared plus b squared, but c is 2, so I'll have 2 squared is equal to a squared plus, now since a is equal to b, I don't have to use that other variable, I can just say a squared. So I'll have 4 is equal to 2a squared. We'll just solve this for a. So divide both sides by 2, I'll have 2 is equal to a squared. Take the square root of both sides, the square root of 2 is equal to a, which apparently is also equal to b. So tying this back in, because I don't really want a and b, I want a squared and b squared when I go back to my main formula. So my a squared is 2 and my b squared is also 2. Okay, so now I can pull this back in. Move this down a little bit. Okay, so I'll have, now my h and k are 0, so I don't have to worry about those. So I'll have y squared over 2 minus x squared over 2 is equal to 1. And there is the equation for my hyperbola. Alright, so I hope you've enjoyed looking at conic sections. It's expanded your mind a little bit. And since we talked about eccentricity before, maybe let's go ahead and talk about it a little bit more right now. Because it holds true not for just ellipses, but you can actually calculate it for all conics. So as a reminder, the eccentricity, spell that a little bit, is E, and it's calculated by doing C over A. And we can tell this, or this computation tells us how close to kind of quote-unquote a circle we are. Where a circle has eccentricity of 0. Now for hyperbolas, since the foci are further away than the vertex, and the distance from the foci is C, and the distance to the vertex is A, on these ones we have that C is going to have to be greater than A. So if C is a bigger number than A, then for hyperbolas, when you calculate their eccentricity, you're always going to get a number that's bigger than 1. And you can play around with this, but if you get a value for hyperbola that it has an eccentricity that is close to 1, this is going to kind of curve away quickly. It's going to be very bendy. So maybe as an example, let's see if these are my coordinate axes. Right, so something that's going to bend a lot. Okay. But as E gets bigger, you're going to get those straighter branches. So as an example, maybe something that doesn't really curve at all as it's going out to meet those asymptotes. So I can still calculate these eccentricities and they still tell me some information about what's going on with my conic section. In this case, this is what's going to be going on with a hyperbola. So I hope you've enjoyed looking at some of these properties and these characteristics of these different conic sections. But if I'm also honest with you, conic sections tend to be a little bit difficult for most people. It's something that you've never seen before, and there's a lot of different nuances going on with the different conic sections. So if you find yourself feeling lost at all, remember to reach out and ask for help. Practice a lot, do a lot of examples, ask a lot of questions, and I guarantee you a lot of this stuff will start making sense, especially if you start really diving into it. Don't memorize formulas and really dig into having a good understanding about what's going on with these distances and how all of these structures relate to each other.